In this OGE, we are going to learn one of the very powerful technique of finding limits called the L'Hopital's rule. The result was introduced by John Bernoulli in 1694, and L'Hopital published this result in his book 1696. So we use the L'Hopital's rule when we have what they call the indeterminate forms of two special types. So when x goes to a, when x reach a, if the ratio fx over gx goes to a ratio of 0 over 0, that means the top function goes to 0, the bottom function goes to 0 also, or the top goes to one of those infinities and the bottom also goes to one of those infinities. In these two cases, we use the L'Hopital's rule. So let's look at this problem. So find the limit when x goes to 0, x minus sine x or x cube. So we have this problem. So let's see what kind of problems we have here. So you can see that one of the way to solve limit problem is the direct substitution. You just substitute the values, and if the value exists, then there's a limit. But that technique does not work here, because if you try to plug in 0 to the top and the bottom, since sine 0 is 0, since sine 0 is 0, you get 0 over 0. So you get 0 over 0. This doesn't have a meaning in mathematics. So that means direct substitution does not work. So the next technique what we normally use is what they call the cancellation argument. So cancellations, you cancel the common factors. That technique also does not work for this problem, because the reason is we don't know how to factor a sine. So we don't know how to factor sine. So don't know how to factor sine. So that means we get stuck with those two common techniques. So that means we need a new method. So the new method is the Bernoulli rule, or the what they call the L'Hopital's rule. So let's look at the rule. I'm gonna call it like Bernoulli rule because he's the one who introduced the result. So what it says that if the limit when x goes to a, fx over gx, there are two functions. The two functions goes to 0 over 0. The top function goes to 0, the bottom function goes to 0. Or the top function goes to plus or minus infinity, one of the infinities, or the bottom function also goes to one of those infinities. In this case, if this is the case, then we have a very interesting result. So what the result is, the original limit, the limit when x goes 0, fx over gx is a ratio, is equals to the ratio of the derivatives. So we take the limit of the ratio of the derivatives. So we take the derivatives of these functions separately, and then we take the quotient, and then take the limit. So this is not the product rule. This is not the product rule. What we do, so it's like you take the derivative of the top function, we take the derivative of the bottom function, and then we divide the two and then take the limit. If this limit exists, so we don't know whether this limit exists or not. If this limit exists, then they are equal to each other. So it's like a very powerful result. So we can do so many things with this one. So let's start to see how we can solve the problem that we were talking about. So let's go back to the problem. The problem is find when limit x goes to 0, x minus sine x over x cube. So as we discussed before, and we know that sine function goes to when x goes to close to 0, you can see that it's 0. So we know that because the sine function is like this. So it's going to go like that. So that's how the sine function behave. And you can see at 0 it is 0. So and then bottom is clearly 0. So that means this is like a nice candidate for the L'Hopital's rule. So let's see what happened now. So it's a limit when x goes to 0, x minus sine x over x equal, and you can see, so we check that you get the 0 for the top and 0 for the bottom. So this is 0 over 0. So now what we can do, we take the limit, we take the derivative. So we take the limit when x goes to 0, just take the derivative of the top. So derivative of the top is 1 minus derivative of sine is cosine, so cosine x divided by so 3 is missing, So 3x squared. Now see whether this limit exists. So when you plug in 0 again to the top and the bottom, since cosine 0 is 1 now, so we know that the cosine 0 is 1. Because of that, now again you get a 0 0. So it's 0 0 again. Since this is 0 0 again, what we do, we use the result again. So let's use the result again. So it's a limit x goes to 0. So we take the derivative. Derivative of cosine is negative sign. With this negative sign, it simply becomes sine over 6x. Now again we know that sine 0 is 0 as before. So this is again 0 0 again. So that means you get 0 0 again. So we write it like that. So just to make sure that we check the condition. So you can see we can take the derivative again. So we take the derivative again. So we take the derivative of sine, this is cosine x, and this is 6. And now we check the value. We see whether this can exist. So when x goes to 0, we know that the cosine 0 is 1. We know this one. Cosine 0 is 1. So that means the final answer is 1 over 6. So that's the reason why this limit is 1 over 6. And so this is like a kind of example of what we normally do in the L'Hopital's problem theory and the problem video. So if you need to know more about that, and you can find the main theory video and the problem set in the description. So thank you.